Assalamu alaikum. As I was saying that if we have continuous attenuation line in the left side plane, then it should give a circle inside the unit circle. Similarly, if it is outside, if it is in the left half plane, sorry, in the right half plane, in that case, it should give us a unit circle that will be have a radius larger than the unity. So basically, a circle that will be outside the unit circle. Okay, so sometimes difficult to draw using the pen. So somehow, say just say this one is your outside one. So this is your unit circle. This is with radius sigma 1 and the other one is with radius e to the power t sigma 2, where sigma 2 lies on the right half plane and sigma 1 is in the left half plane. So now with the similar article within the similar topic, we can also find out the settling time. Settling time TS. So we want to find a zone with the settling time of lesser than a particular given value. So that this is your sigma 1. And we know that from the formula from the classical control that sigma is TS is related to 4 by sigma. And now higher the value of sigma, lower the value of TS. So if you're given a particular problem where they're saying that the settling time has to be lesser than 0.1 second or maybe 1 second, so any particular value. So corresponding sigma value you have to find, and the higher values of sigma will give you lower values of TS. So basically we are talking about this zone of operation. Okay, so how can we find out this zone? Again, we know that we should have the unit circle as well as we should have, because of the sigma 1, we should have another circle inside. And we know that this zone is corresponds to lower value of sigma. So basically, it will be inside this the smaller circle. So that corresponds to where the boundary is actually e to the power t sigma 1, and inside you have the lesser value than that. So basically, smaller or lesser settling time will be inside the small circle. Well, the next thing that we should discuss in the mapping is the constant frequency locking. Constant frequency. Okay, so basically the locus, plural of that, as we already say. Now, basically the horizontal lines, if you have in the S-plane, so horizontal like this one, always keep in mind that the boundary may be j omega s by 2 to minus j omega s by 2. How they're related? We know that this is related to minus pi and this is related to pi. So any vertical, any horizontal line, say this one, say it is related to your j omega 1, and any line closer to that one as well, so j omega 2. So how can we represent that one? So in the z plane, how they're represented is basically, so as you can see, the magnitude wise, the magnitude here plus, so a very high, maybe infinite magnitude, to you're coming to a unit magnitude at this particular point if you travel through this line. Okay, so then eventually it will be 0. Okay, so or and if you move in the other way around as well, no problem. You will have the same thing from 0 magnitude up to infinite length. And now, as you can see, since definitely it is lower, lesser than half of your omega s by 2. So you can, here you can have omega s by 4, or which corresponds to actually pi by 2. So this value has to be lower. So it means you will have lesser than omega pi by 2. So you're going to have a line like this. So this is your constant frequency line, and it is related to z e to the power t. By mistake, I sometimes may have said tau, but it is actually t sigma plus j omega 1. Okay, now the other one is very close to minus pi by 2, basically greater than minus pi by 2. Okay, so greater than minus pi by 2, it means this is your pi by 2 line, minus pi by 2 line. So it has to be somewhere here, somewhere here. Okay, so one line may be there and the other one is here, and this is related to z equal to e to the power t. Okay, so any value of sigma you can take, and based on that, the height, the length here will be depending on that plus j omega 2. So this angle actually, as you know, that omega is related to angle. So t omega 1 and t omega 2, they are the angles. So based on that, you can calculate these angles. Okay. Now, can we relate this with, since we know constant frequency line as well as constant attenuation line, so can we figure out what will be the scenario for this particular case? Like we are giving a zone, we are giving a zone like this, and we have to figure out the corresponding zone in the z plane. So this is in the s plane. To value given, this is omega 1, j omega 1, j minus j omega 2, as well as this is your minus sigma 1, and this is your minus sigma 2. So now, how can we represent these two in the z plane? So in the z plane, we know that these are related with circle, and definitely this is since omega 2 is smaller than omega sigma 2 is smaller than sigma 1. So this will be inner circle and this will be outer circle. So inside the unit circle, if you want it for a reference, you can draw it. Otherwise, two circle you have to draw. Both of them has to be inside the unit circle. Okay, so two circle you'll have, both of them inside the unit circle. Now, here comes, now this is related to your sigma value. So this is related to your sigma 1, and the other one is related to your sigma 2. The next thing is now comes angle. So definitely say you need to know what is your omega s by 2 and plus and minus omega s by 2. This is what you should know. And once you know that, based on that, you can find out what is the angle here. So this is basically pi, very close to pi. Okay, so basically very close to pi. You can draw a line like this, straight line it has to be. And the other one is lesser than half. So basically lesser than half is minus pi by 2, lesser than minus pi by 2. So somewhere here maybe you will have it. Okay, so what you can see is that the zone here is bounded by these two. That means these two circle, as well as these two angle. So the t omega 2 to t omega 1. And we know that this shifting from one to another is actually a counterclockwise representation in the z plane. So as you can see is that this particular zone within that two frequency line, as well as within the unit circle, the two circle that is specified by the two sigma, is actually corresponds to this particular zone. Okay, so this is t omega 2, and this is related to t omega 1, and this is related to sigma 2, and this is related to sigma 1. So in between that boundary, the zone that we are getting is actually specified by the zone in the S plane. Okay, now next thing is constant damping ratio lines, locus or loci. So constant damping ratio loci. So we know that. Let us go with a bit of formula first, then we'll try to see according to the figure how it looks like. So S equal to minus zeta omega n plus j omega n 1 minus zeta square, which is nothing but actually your sigma d and omega d. Okay, so we can also write it as minus sigma d plus j omega d. Okay, so we can write from the z equal to e to the power ts. If we replace these two value there, an exponential of minus zeta omega n plus j omega d. You can also give the t inside, no problem. Okay, so now how can we simplify a bit? Now let us introduce. So minus zeta omega and t, we can actually introduce in the angular part is omega d, t by twice pi. T by twice pi also introduce twice pi. T by twice pi is nothing but omega s. So as we know that our design in the discrete time or digital control system is heavily dependent on the sampling frequency, because the pole and zero location can change based on the values of your sampling frequency. So we always have to keep in mind. So that is why we want to represent the frequency with respect to that sampling frequency. Don't forget twice pi. Okay, so this is how the angle is being determined. Now, can we also find out the magnitude as a ratio of the sampling frequency or not? So, but if you can introduce the same thing here, like omega d and omega s here as well, so that will be helpful to plot the line. So let us try to do that deliberately. If you want to bring omega d, then you have to have omega n into 1 minus zeta squared. So that is your omega d. So which is 1 minus zeta is not available. So you just give it there. And also to bring t, what we have to give is to being omega s, to t must be divided by twice pi. So you have to multiply with twice pi as well. Then the rest of the thing, twice pi omega d by omega s. So finally, we can write something like this: e to the exponential of minus twice pi zeta by 1 by zeta square. Don't forget the root over into this is 1 by omega s. So basically omega d by omega s plus j twice pi omega d by omega s. Okay, so as you can see, this is your okay, so this is your real part, and that will be related to your magnitude, and this is your imaginary part. And that has to be related to your angle. So you can say that magnitude of Z will be exponential of minus twice pi zeta divided by root over 1 minus zeta square omega d by omega s. And the angle is zeta equal to twice pi omega d by omega s. Now, since we know this too, now if you want to find out the constant zeta line, we know that in the z plane it represents the diagonal lines. So in the z plane, these diagonal lines represents constant zeta line, and always we have to keep in mind your omega s and omega s by 2. So omega s by 2, omega s, say we have few other parameters like omega d. So these are corresponds to two things. One is your frequency or angle as well as your magnitude. Okay, so this is what we have to keep in mind. Both of them are actually involved. Okay, so they're related with your sigma 1, sigma 2, and sigma 3. So sigma increasing means in the left half plane means your magnitude is decreasing, and frequency increasing means actually your angle is actually also changing. So basically this is where it is 0, this is where it is pi, this is where it is twice pi, and also increasing values. Okay, so uh, at magnitude, how can we find out the magnitude? So say for any particular value of zeta, they have used zeta equal to 0.3, zeta equal to 0.3, what will, and we are saying that omega d equal to 0.25 of omega s. So in this particular case, what will be our magnitude? Magnitude of z will be exponential of minus twice pi into 0.3 zeta value divided by root over 1 minus, sorry, 1 plus 0.3 whole square into 0.25. So at any particular point, we can figure out the magnitude 0.61. Okay, similarly at, and what will be your angle at that point? Angle will be given by twice pi into 0.5, 0.25, that is basically 0.5 pi or pi by 2 or 90 degrees. So what we can find is that at this particular value 0.25 of omega s, this is the relation we find. Okay, so if we plot these corresponding points on the z plane, then what are you going to get? First one is here, so angle is 0, magnitude is 1 because e to the power 0 is 1. So what we are starting with is If you draw your unit circle as a reference, okay, so we're actually starting from this particular point. Okay, so this is your point 1. So point 1, then 2, 3, 4. So what will be your point 2? Omega is at 90 degree. We are getting 90 degree with a magnitude of 0.6 something. So we'll be somewhere here. Okay. And if you plot similarly for omega d equal to 0.5 omega s, and then you're going to find the magnitude. Just follow the formula 0.3725, and the angle you are going to get is pi, that is 180 degrees. So you're somewhere here with a magnitude of 0.37. So you're getting a magnitude something like this. Okay, so gradually you'll find a spiral kind of shape, logarithmic spiral. So you'll find a constant zeta line, something like this. Is it okay? So it will be based on the calculation. So you don't have to worry too much about how the thing is coming, rather just follow the step. Okay, so next thing is, and this is for a particular value of zeta. Now, what will happen if you're changing the zeta values, and then how the shape will be changing? So for different values, you have to experiment with, and eventually you will see that zeta equal to 0 is the unit circle itself. So zeta equal to 0 is your unit circle, and zeta equal to 1 is this particular one. So here you are going to get zeta equal to 1. So other in between, from gradually if you start increasing the zeta, then you're going to see shapes like this. Okay, so shapes like this you're going to, I'm just drawing the half of it, not the whole thing. So you say zeta equal to 0.2, zeta equal to 0.4. So this is how you're going to get the rest of the figure. And the downwards is just the identical. So you can just draw in the similar way. Okay. So this is how you have to find out. Now, one other thing we have seen about constant omega n line. We know that omega n, this diagonal line is actually your in the S plane. Plane, this length here is represented by omega n, and this angle theta related to your zeta is cos theta. Okay, and now if you draw your constant omega n line, which will be eventually a circle, and as you can see, the circle is always in 90 degree with that one. Now, if you have drawn a constant zeta line which starts from 1, and you have a petal spiral pattern like this, now what will be, and for different values of zeta, you're going to get different values. For higher values, eventually it will be a unit circle. Now, if you want to find out that omega lines, so omega lines also should start and follow a 90 degree angle with each of them. So it has to be 90 degree here, it has to be 90 degree here. Okay, so and also it has to be 90 degree here. So you'll follow a path like this. So more appropriately, if you want to look at that one, you better see your example, figure 4.9. It will give you a better picture what is happening there. Now, example 4.1, they have given a zone. For example, 4.1. So they are giving particular zeta lines. And they're saying that try to find out the corresponding mapping in the Z plane where you're actually interested about this area. Okay, so how can we find out that particular thing in the S plane? So what we know so far is that here the zeta values. Well, from the zeta value, we know that if you go in that way, your zeta will be smaller and smaller values of zeta. Why? Because cos theta, the angle higher, the zeta value is smaller. And you go in this direction, your zeta will be higher. Okay. And from also these figures, we know that the relation with higher, lower values of zeta is your unit circle, this zeta equal to 0, and higher it is becoming smaller gradually. So if you want to represent this zone, what you have to do, you have to draw a zeta line corresponds starting always from 1, a smaller one. Okay, and since you have two lines, so you have to have an identical line in the other one as well. Even though it will be spiral, my ones are not. It should be a bit logarithmic spiral, something like this. And similarly, you will have identical in the other way around. Now, since in this zone, the zeta value is higher, so also you have to, your higher zeta value will be inside that spiral, logarithmic spiral kind of shape. Okay, so this is your 1, starting from 1. And always it is better to actually draw the unit circle to have the particular reference. Okay, so this is how, using the example 4.1, even if you don't solve it with proper equations, you will have a shape like this. Okay, the last one is if you extension of your example 4.1, they have given constant zeta lines, 2 zeta lines are given, as well as they're guided by the omega lines. Okay, so they are guided by omega lines. So this is j omega 1 and identical. So on the other way around as well, minus j omega 1. So two zeta values, zeta 1 and zeta 1 both are same. And also, since we are interested about this particular zone, my drawing is not proper, but it has to be something like this, and they are also be controlled by this zeta lines. So sigma lines, sigma 1. So actually, we are interested about this zone. So how can I predict? So first of all, is there the eraser? Okay. Okay, so now, first of all, what are the things that you have to look is, first thing is your sigmas, the sigma is related to your circle. So this one will be related to a circle, and we are actually moving to this side, so inside the circle. So this is one thing. Okay. Second thing is they're governed by two frequencies, same frequency. So there'll be a zone as well specified by two lines. And similarly, these zeta lines, they are also actually blocking, the zeta lines are actually blocking your spiral nature. So you have to draw, first of all, the unit circle as a reference, the unit circle as a reference. Then the two omega lines, say these are our two omega lines. Obviously, they'll depend on how close they are from j omega s by 2. So say these are the two lines, since they are same, so they'll be identical. And then the zeta line that you was given, that you also have to draw the spiral lines. Something similar will be in the other way around as well. Okay, and finally, what we have is our sigma. So you should also draw a circle. Inside the circle, the parameters should be there. So say with This is the value of the circle we are getting. Okay, so these are all parameters. So inside the circle governed by these two as well as with the zeta line. So based on that, what you can see is that, let me change the color a bit, it will be easier to figure out. Okay, so what you can see, the common part is in this portion. Okay, so governed by these angle lines, governed by this sigma line, governed by this zeta line, is a common part is this particular portion. So this will be your zone of operation. Okay, again, I'm sorry about this circles. It's very difficult to draw in the Wacom using this one. So this was your article 4.2, that is mapping between your S and the Z plane. Next, we'll start article 4.3, that is stability analysis of the closed loop systems in the Z plane. Okay, see you inshallah in the next class. Assalamu alaikum warahmatullahi.